Let's review Kirchhoff's laws and look at some mixed circuits. Before we look at the mixed circuits, let's just do a quick review of parallel and series and what Kirchhoff's laws mean for parallel and series. I put a quick summary at the top of how we apply Kirchhoff's laws to series and parallel circuits. So this is just a reminder. In series, current is the same everywhere because we have just one path, where in parallel, the current splits between the paths. And for voltage, in series where there's just one path, the voltage drop in each load has to give us the total voltage. Whereas when there's multiple paths, the voltage drop in each path is equal to the total voltage. And then we have our resistance calculations. So I'm going to start with both a parallel and series circuit and that we've built and just go over how these laws apply to them. So we have two circuits, one in parallel and one in series. And both of them have two 6 ohm resistors connected to a 3-volt battery. The parallel, they're just connected around each other, so there's two paths. And in series, they're connected one after the other so that they are beside each other and there's only one path. So Kirchhoff's laws aren't worded exactly like this, but these are an easy way to think of them for both series and parallel. And that's that the voltage drop in any one path has to total the voltage drop here. So in parallel, the voltage drop will actually be the same for every single path. So this first path right here will have a voltage drop of 3 volts as well. And then the voltage drop in the other path will be 3 volts as well. So no matter which path those electrons take, they're going to lose all 3 volts, come back to the battery, gain 3 volts and go back through one of those paths and lose all 3 volts. So no matter what path they take, they have to lose the voltage of the battery or the total voltage. In series, though, the voltage, because there's only one path and the electrons are going through both of these, it's not going to lose 3 volts at this one and then 0 volts here. It'll lose some voltage here and a little bit more here, so the total voltage lost between V1 and V2 will be equal to the total voltage, which is 3. We're not 100% sure what that total voltage is. We kind of can figure it out in this case because our resistors are the same. They'll split up equally, but a lot of time we won't have the same resistor, so we might not be able to automatically know what these voltages are. But what we can do for both of these is find the total or equivalent resistance. For this parallel circuit, if we're going to find the total or equivalent resistance, I want to use this formula where I have 1 over equivalent resistance is equal to 1 over R1 plus 1 over R2. And then for series, the total resistance, if we look at the series properties, is just adding, we can add up each individual resistance to get the total. So we'll have RT is equal to R1 plus R2. In this case, it's 6 plus 6. So that's actually a pretty quick one to add together and get. That gives me 12 volts. And if I sub in here, 1 over RT is going to be 1 over 6 plus 1 over 6. And you can actually divide these and get the decimal, but it's probably easiest just to add the fractions and get 1 over RT is equal to 2 over 6. And then we'll use our little trick. If we want RT on the top, we can flip this, but we have to do the same to the other side. So I'll flip both the top and the bottom, and I'll get RT over 1 is equal to 6 divided by 2, which is equal to 3. So the total resistance in this circuit is 3, and the total resistance in this circuit is 12. And that makes sense. If I put more paths in, it actually decreases the resistance. So I'm taking my 6 ohm resistor, and the more I put more paths for the electrons to go through that 6 ohm resistor, it decreases the resistance. Whereas if I put them beside each other, they have to go through more resistance. They have to go through one then the other. So you get a higher resistance when you put multiple resistors in series. Once I know RT, or the equivalent or total resistance, I can find the total current here. And to do this, we will use Ohm's law. And I'm going to use the version of Ohm's law to find current. So I'm going to come up here and use current is equal to V over I. So if I want to find the total current, I'm going to take, V over R. V over R, which in this case is 3 over 3. So in that parallel circuit, the current is 1 ampere. And in this circuit, V over R is going to be 3 over 12, which will be 0.25 if you do that on your calculator. And then the last thing that I want to do is find the current at different spots in the circuit. So because I know if we come up to what our little summary says about parallel circuits, the current's going to split. So I'm starting off with 1 ampere, and it will split between these two. If you have different resistances, it's not going to split equally. If you have the same resistance, it will split equally. So in this case, you will have 0.5 and 0.5. And you could also do for 1 V over R, and you can see if I take 3 divided by 6, you can type that into your calculator, and you will get 0.5. And the same thing for I2, our V is 3, and our R is 6. So if I divide it, I will get 0.5 as well. In this case, my voltage, remember from this summary up here, my voltage actually is going to drop some here and some here. Now, because these are equal resistors, they will actually split. The voltage will split evenly here. And the other thing to notice is that the current is the same everywhere. Everywhere in this path, it's going to be the same. There's no splitting of that path. So I know the current is here in 1.25. And in 2, it's also 0.25. And the total is 0.25. So if I don't split, the current's going to be the same everywhere in that path. And I could calculate the voltage. I could take, to do that, to find voltage, I would take my V is equal to I times R. And if I do multiply V equals I times R, you should get 1.5, which you do. 6 times 0.25 gives you 1.5 volts. And the same here. So that's how we can analyze series circuits and parallel. We're going to apply this to mixed circuits. So we don't always have nice, easy circuits where there's only the resistors in parallel or only in series, sometimes they do get a little mixed up. And then we want to be able to figure out at least our total resistance and total current in that circuit. So now if we have a circuit where we have mixed series, so we have something that looks like it would be beside that one resistor here, but instead of just being beside one resistor, we now have two resistors in parallel. We're going to have to combine what we know of parallel and series circuit. So we'll start off with just finding the equivalent resistance. The first thing we want to do is make it similar to that last circuit where we had just one resistor here and one resistor here. So we're going to take this parallel circuit and kind of break it down and make it like one. If we want to find one equivalent resistance for this. We can call it RT, but that can get a little bit confusing because that might be the total of the whole circuit. So I think I will call this R between 2 and 3. So the equivalent resistance of combining 2 and 3. Because these are in parallel, if we want to combine resistors 2 and 3, we're going to have to use this formula right here, where we take 1 over R total, but the total is just going to be for 2 and 3, not the whole circuit. And we're going to add 1 over R1. Oh, but in this case, the first one is R2 and 1 over R3, the two that we're combining. So we're just taking this portion of that circuit that's parallel and finding a resistance that we can think of it as 1. And if we do that, we would end up with 1 over R2, 3 is equal to 1 over 12 plus 1 over 12. And again, you can use your calculator and turn these into decimals to add them, but I actually, if I have the same denominator, you can just add the top. So if you have the same bottom number, which here is 12, I can just add the top. So it's 2 over 12. So 1 over R for resistors 2 and 3 is 1 over 12. And then we'll flip both sides. So resistors 2 and 3 over 1 will be equal to 12 divided by 2, or 6 ohms. So these two resistors in parallel is like having just one resistor of 6 ohms, which was like our last series circuit where we had 6 ohms and 6 ohms right beside each other. So this right here is just like having a resistor of 6 ohms between those two. And then we can treat this like a series circuit, which we just did in the last example. So we can find the total resistance. And since if we count this as one 6 ohm and a 6 ohm beside each other, that's like the series where we would add it to get the total resistance of the circuit, and that total resistance would be 12 ohms between those two 6 ohms. We also want to be able to calculate the current in this circuit, and the current here is going to be, we don't know it right off the bat, but we can figure it out because we know voltage and we know resistance, so we can find the total current. I'm just going to take Ohm's law, and I'll use this version of it where current is equal to voltage over resistance, and we'll make sure we use the total. So that's going to be 3 over 12, or 0.25, which is actually the same, because this is just like, that's the same as our last example, because in our last example we did have a 6 ohm and a 6 ohm resistor. And that gives us the same current. Let's try a slightly different one that's also mixed. So there's both series and parallel. Now in this case, it's a little bit different. We have This looks like our parallel circuit, except instead of just one resistor over here, we have two. So we can't just analyze like two of these in parallel. We have to account for this one right here and this one right here. So what we'll do is this time we'll combine these two. Then we'll have something that looks like our parallel circuit where this will be combined as one and with this one. So I'm going to combine R2 and R3. Now, in this case, they're beside each other or in series. So it is actually a little bit easier to combine them. We can just add their resistances and find what the total resistance for these two are. So I'll just call this, that's the total resistance of just 2 and 3. And we'll, just to shorten it, do 2 and 3. And we just add, because they're beside each other or in series, we're going to add those. So I'm going to get 3 ohms plus 3 ohms. So because there's 2 3 ohms right beside each other, it's like just having one resistor that's 6 ohms here. So now it's like having a 6 ohm resistor, and if we combine these two in parallel with another 6 ohm resistor, and we can find the equivalent resistance for the whole entire thing. So we've combined these two. Now we want to find the equivalent resistance for that whole entire circuit. So we'll take this resistor and combine it with, sorry, I'll get my pointer. We'll take this resistor and combine it with this combined resistor. Since these are in parallel, this is actually just like that parallel example I did, we'll have to use the 1 over RT. So to find the total resistance, we'll use 1 over RT is equal to, sorry, I meant to put an equal sign there, 1 over R1, and then we're going to use that combined red as our second resistor. So it's like we have just the two resistors in parallel. And that would be 1 over R 2, 3. We don't have a formula for like 2 in series plus 1 in parallel, so we have to use this way of combining, simplify one part of the circuit that can be simplified, and then we can use our next formula. So 1 over RT is equal to 1 over 6 plus 1 over 6. And that's going to be 1 over RT will be equal to 2 over 6. And then what we want to do is find RT. And we can't, we'll have to flip this, but we can't flip this side without flipping the other side, so we'll flip both sides. And RT over 1 will be equal to 6 over 2, or RT is 3 ohms. And then our last step would be to find current. And we can do that. We don't know what current is, but we know R and V, so we can use our form of Ohm's law where we can divide V by R, and it will give us the current. And that ends up being 1 because resistance is 3 and our voltage is 3. So that's how we can analyze mixed circuits to give us our overall resistance, and then we can use our overall resistance of the circuit to find current.